Aloha, and welcome to Live from NOIRLab at Gemini. My name is Jamika Marshall. I am an outreach assistant here at the International Gemini Observatory here in Hilo, Hawaii, which is a program of NSF's NOIRLab. Today's moderator in the YouTube live chat is Outreach Assistant Alyssa Leilani Grace, who will share your questions and comments with our guests throughout the show. So please post your questions and comments anytime throughout the show, and Alyssa will come in throughout the presentation to share with us your comments and your questions. Now, before we meet today's guest scientist, I'd like to tell you a little bit about the International Gemini Observatory. So the International Gemini Observatory is one of 5 programs of NSF's NOIRLab, which is the preeminent U.S. National Center for Ground-Based Nighttime Optical and Infrared Astronomy. Now, Gemini Observatory is composed of twin telescopes, here Gemini North, located on Mauna Kea, and the other is Gemini South, located on north central Chile's Cerro Pachón. Now, each Gemini telescope has a mirror diameter of 8.1 meters, or about 26.5 feet. Now, with a telescope in each hemisphere, the International Gemini Observatory can observe objects throughout the entire night sky.
Aloha, Jamika. Can you please share the slides with our wonderful audience?
Now, a little bit of Gemini news. Gemini, last week, we talked about our newest press release on Jupiter. Now, this was the May 19th press release, and it was featuring a beautiful image of Jupiter. Oh, I believe I'm not screen sharing. Let me do that right now. So beautiful image of Jupiter. I apologize here. There is a link to this press release and further article in the video link description below. Now, for our user communities, the 2020B observing tool is now available. Now, this Gemini observing tool is available for download. Now, this is an update that's required to access the Gemini observing databases. The installation instructions are actually linked on the Observing Tool webpage. So for all of our users, go ahead and check out the science operations announcements on Gemini's webpage, which will be linked in the video description. Now to today's special guest. Our guest scientist today is none other than Dr. Tom Geballe. Dr. Geballe will be joining us here in just a moment when he enables his share screen. And while we're waiting for Tom to join us, let me go ahead and give you an introduction to Dr. Geballe. Now, as I've been working with him over the past few days to get to know him a little bit better, I found him to be just absolutely fascinating. So now, Dr. Geballe actually is an emeritus astronomer at Gemini North. And as we were talking, I definitely wanted to ask him what an emeritus astronomer is, and he's going to fill us in on that shortly. But he earned both his bachelor's degree and his PhD in physics from the University of California at Berkeley in 1967 and 1974, respectively. following 3 contemporary research positions at Berkeley, Leiden, and then Pasadena, he and his family moved to Hawaii in 1981, where he worked as a staff astronomer and actually head of operations at the United Kingdom Infrared Telescope, and that's actually in the Summit region of Mauna Kea. And that was from 1981 until actually 1998. And that's right before he moved to the Gemini Observatory. So, Tom, thank you so much. Welcome. We're glad to have you here with us today.
Thank you very much. I'm very glad to be here. And let me just ask now, is my screen being shared? Because your screen was never shared.
Can you hear us, Tom?
Yes.
Yes. Okay, fantastic. Thank you again for joining us today. And apologies to our YouTube live audience. I had to snafu with my share screen, but we are here with Tom Geballe right now. So Tom, one of the things I learned that I found interesting about you is that even though you have two degrees here, you actually did not take any astronomy classes. How does one become an astronomer and know so much about astronomy without taking any astronomy classes?
You learn it, Jamaica, by doing it. Are you hearing me, by the way?
Yes, we definitely can hear you.
Good. All right. Okay, yes. You learn it by doing it. I got into it because I worked for a professor at Berkeley, Professor Charles Towns, who was a physicist, but was very interested in expanding astronomy into wavelength regions where people were not doing it, especially into the infrared and sub-millimeter. And so I was, my graduate thesis was about building a spectrograph for the infrared, one of the first ones that was ever built. And I just picked up astronomy by using it and doing it at telescopes. And I've done that with, of course, I've had a lot of help from the people with whom I collaborate who are real astronomers. So I just picked up astronomy over the course of my career.
That's been a very long-ranging career here. And so we are very much appreciative of you being with us today. So now the title of your presentation is Extremely Overabundant Oxygen-18 and Hydrogen-Deficient Carbon Stars. So I take it we're going to talk a little bit about star formation.
Well, in a way, yes, but this is not, this isn't your mother's star formation. You know, everyone thinks that star formation, or most star formation takes place when a cloud of gas and dust collapses and forms one or more stars. This is a different type of star formation than that, and so it's quite different and a kind that people hadn't really envisioned until very recently.
Well, we are in your hands, Tom. So take us on this journey to explore these very unusual stars.
Okay, I will do so. Let me just make sure, is everything set for me now?
Appears to be, Tom.
How do I, okay, very good. All right, so yes, extremely overabundant, let me get rid of this. Extremely overabundant oxygen-18 and hydrogen-deficient carbon stars and our corona borealis stars. Now, this talk is not about something that was just discovered, but about a discovery that was made about, well, actually began about 15 years ago, in which I was very fortunate to be involved. And my goal in this talk is not just to show you some interesting science, but also to give you an idea of how astrophysics progresses, that it can start from an accident. How progress can involve many different people with different types of knowledge, not just the observers like me. This talk also involves spectroscopy, which is, I think you know, measuring how the amount of light changes with wavelength. And that's really how we learn most of what we know about the universe. And it's also about these two classes of stars whose names are in the title. And in the image, you can see one of these, you can see the prototype of one of these, the star R Corona Borealis, the namesake of that class. I will probably call it RCB at times, or I might even call it Arc or Bohr. It's definitely not a boring star, or any of the stars in its class.
So Tom, here in your image, anyone who's kind of familiar with the sky at night right now will know that the corona borealis is out around Hercules. So
Yeah.
the CRB, is that the named for
That's the way astronomers write the name of the star. Any
Okay.
star in corona borealis will have the CR, capital C, small r, and then capital B.
Okay.
Yeah. All right, let me continue then. So if you read the title, you probably see some other words that you might not be familiar with besides those funny star names. And the first question might be, what is 18O, or oxygen 18 as it's often called? Well, the answer is that it's an isotope of oxygen. And then I guess your next question might be, what is an isotope? And this slide attempts to answer that question. And the main point is that each element, hydrogen, helium, carbon, oxygen, nitrogen, so on, has a certain number of protons in its nucleus. You probably already know that. But an element may have different numbers of neutrons in its nucleus. And nuclei with the same number of protons, but different numbers of neutrons are called isotopes of the element. So chemically, the element behaves the same way regardless of how many neutrons the atom has, but its mass is different, of course. And the simplest examples here are in the pictured in the slide. A hydrogen, which has only one proton, it exists in two stable forms, one proton and no neutrons. That's the common form of hydrogen that we know. But there's another form called deuterium, which has a proton in the middle. And there's actually a third form, tritium, which is radioactive. So there's really hardly any of it available on the Earth, but there is deuterium on Earth in the atmosphere. Another example is helium. I show that there's two stable forms of that, one with one neutron, one with two neutrons. Now I'm going to be talking a lot about carbon monoxide in this talk. That's CO. And carbon has two stable isotopes, carbon 12 and carbon 13, with 6 protons and either 6 or 7 neutrons. And oxygen has 3, oxygen 16, 17, and 18, with 8 protons and either 9 or 10 neutrons. The C12 and the O16 are by far the most common isotopes of those elements, as you can see at the bottom of this slide.
So, Tom, what actually makes some of these isotopes rare and others not so rare?
That is a good question. I'm not sure I can answer that very easily, but it's just, I think I'll have to skip that question, Jamika. Maybe I'll come up with the answer later.
All right, we'll follow up with you.
Okay. All right, so there are 2 stable isotopes of carbon, as I just mentioned, and 3 of oxygens. And that means there are 6 possible types of carbon and oxygen, and those are called isotopomers of CO. And this slide includes their abundances relative to one another on the Earth, in the atmosphere of the sun, and in stars known as red giants, which seem to have a lot of carbon-13. We know why that is, but I'm not going to get into it right now. A key point, as you can see, the C12O16 is by far the most common. C13O16 is fairly rare, but and the others are extremely rare because those isotopic species of carbon and oxygen are very rare. So combinations of them are even rarer. A key point here is that we use CO to measure abundances in stars, and that's because CO vibrates. It kind of acts like there's a spring between the carbon and the oxygen. And the more massive isotopomers, which are basically the heavier ones, they vibrate more slowly than the lighter ones. And that means that they absorb and emit light at longer wavelengths than the lighter versions of the molecule. So to measure the relative amounts of those isotopomers, we compare how much light each emits or absorbs at whatever we're looking at. In the case that I'm talking about now, we're going to be talking about absorption. So now I'm ready to start our talk. And I'll start my story. And it began late in the afternoon of November 24th, Hilo time, about 5 p.m. I was about to go home. And at that time, I received an email from Jeff Clayton. He's a professor of astronomy at LSU. He and I had been studying Arcor Bohr stars for several years. It was almost 9 o'clock in Baton Rouge where he was, but something had been bugging him and he decided to ask me about it. So he wrote, "Hi, Tom, I have the spectrum of the first overtone CO bands in the HDC star, HD 137613. That's just a catalog number for a star that was found cataloged a long time ago. I took a look at it and the bands were split. So I said to myself, oh, well, there's 13 CO. but the extra components aren't at the right wavelength. So I'm a bit mystified. Take a look and see if you have an idea of what this is. So what does all that mean? It means that what puzzled him were the sharp dips indicated by question marks. The arrows point to well-known absorptions by C12O16, but he didn't recognize the other dips. They were not at the right wavelengths for C13O16. Well, in about 10 minutes, I had the answer and I wrote back to him. That is amazing. I happen to have a book of CO wavelengths that I calculated when I was a grad student in the 1970s, all the DV=1 and DV=2 lines of all isotopic species. Those bandheads match C12O18. The first three bandheads are at 2.349, 2.378, 2.408. I also looked at C12O17 and it doesn't match. How could a star have this much oxygen 18 as oxygen 16? What kind of a star is this? Cheers and congratulations.
So Tom, here, can we first explain what we're looking at here on your screen here? I assume this is a spectra and the top
spectrum, an infrared, a portion of the infrared wavelength region between about 23,000 angstroms and 25,000, if I can't see the end right now because there's 24,000 angstroms. And so you're measuring the amount of light from the star. The light is sort of decreasing slowly as wavelength increases, but you see these very sharp dips. And some of those dips are well known to almost all astronomers. They correspond to absorptions by carbon-12, oxygen-16. And if you look at the top spectrum, you can see there are other absorptions at about 2.35 and 2.38 and 2.40 microns. They don't correspond to the ones that you normally see in the red giant, which is a spectrum below. The other ones you see in the red giant are carbon-13, oxygen-16. But these ones in this HDC star matched oxygen C12O18. And you can see they're about the same strength as the C12O16 line. So it meant that there was a huge amount of O18 in this star.
Okay.
And O18 is normally 1/500th of all the oxygen. So, yeah. Does that make sense? Yeah.
It does. We are following. Thank you.
Okay, okay. All right, so clearly I was stunned. I'd never seen anything like this. Nobody had ever seen anything like this. There's nothing even close. And I didn't know what an HDC star was. So I asked him, what is that? What kind of a star is this? And he wrote back the explanation. It's a hydrogen deficient carbon star, which means that it looks like an RCB star, which is what we were studying. He and I had been studying, except it doesn't make any dust. All the RCB stars are without carbon-13. So they've had weird stellar burning, but this is even weirder. I was wondering about the other isotopic species. I'm glad you had your grad student notes and so on. And he mentions that he had tried to observe several other stars and never seen anything like this. And then he added a comment. Would you like to write a paper on this? By the way, you already have. There's a spectrum of HD 137613 in Airs et al. 1998, a paper that I was on. The components are blended, but there's a comment that the band strengths are weird. Well, that was a little rude, a little sarcastic, but we always have fun insulting each other. I found a paper, and sure enough, he was right. I was the author of a paper that already included a spectrum of that star in the wavelength region where the C12O18, the CO absorptions are. And the evidence for C12O18 in this spectrum wasn't as obvious as the spectrum he sent me because the resolution was lower, but there's clearly something not normal with some of the C12O16 absorptions compared to the ones over here. These look quite a bit different. So
Tom, here on going back here to what you were asking him, now we're talking about hydrogen deficient carbon stars.
Yeah.
So since we know that stars have to burn hydrogen for fuel, if we're talking about stars that are deficient in hydrogen, does that mean these stars are burned less bright?
That means it burned all of its fuel already. So it's burning something else. That's
okay.
Yeah.
Okay.
Yeah. Okay. It finished with all its hydrogen. Yeah. So anyway, so I made a rather lame excuse, and I offered to help him write about the paper about the discovery. And the other comment I made at the end about the Boston Red Sox, which you can read, I said, I'll bet the ALCS and World Series were quite an experience for you. That's because Jeff is the most rabid Red Sox fan I know. And that year, that month, the Red Sox had just beaten the Yankees to win the American League Championship, and then beaten the Red Sox in the beaten, I don't remember who in the World Series to it was the first time they won the World Series in, I think, almost 90 years. So
I'm sure we'll get some comments about that one. They'll remind us who they were playing.
yes, right. So, right. So then this was the final email tonight, and he pointed out that 37 years earlier, someone had actually predicted there would be lots of O18 in hydrogen deficient stars. And he also responded about the Red Sox, and he promised to make me work, which of course I was very willing to do. It was such an amazing discovery. Okay, so that's the story of the discovery of this. This slide just summarizes what was known about the O18 abundance at that time. In this star, C12O18 was as abundant as C12O16, and that means O18 was as abundant as O16. That had never been seen in any star in the interstellar medium, in the sun, on the Earth, anywhere. So clearly this star was unique.
Tom, when you mentioned the interstellar medium, can you explain to our YouTube audience, to all of us, what that is?
That's the gas in between the stars.
The gas in between the stars is the interstellar medium.
And we can measure carbon monoxide in that gas as well. So it's very easy to measure the relative strength. You just look at a star and see, look at the absorptions, or look at the emission of the gas. Actually, that gas is very cold, but there are certain emissions that it makes, and you can just compare the emission strengths of the various isotopomers and deduce the approximate relative abundances. And basically, it's O18 is very rare in interstellar space as well.
Okay.
Okay. So, whoops, how did that get here? Here we go. All right. So now let me finally explain a little bit about these two types of stars, HDC stars and RCB stars. So first, the hydrogen deficient carbon stars, as their names indicates, they're hydrogen deficient. And since hydrogen is by far the most abundant element in the universe, that's very remarkable in itself. Then they're also carbon stars, and to astronomers, that simply means that carbon is more abundant than oxygen. And they have lots of nitrogen too. What else about them? They're very rare. Only 5 are known. There are probably more, but they're hard to pick out, actually. So there are probably a lot more. They shine steadily. They don't have winds coming out of them. I mean, they might have a very weak wind like our sun does, but they're not much of a wind. And they're extremely luminous. They're extremely bright. So the little graph at the bottom left shows you a plot of temperature of stars versus luminosity. The sun is sitting right here. And up here in this box are where all the hydrogen deficient carbon stars and all the our corona borealis stars, for that matter, all live. So they're up here among the brightest stars like Betelgeuse, like Rigel, things like that, stars like that. They're brighter even than most red giants.
Tom, this graphic that you're pointing at here in the bottom left of your slide, is this the Hertzsprung-Russell diagram? That,
in a way it is, yes, in a way it is. It's usually plotted in a different way, but it has the same shape, and that's basically because it is a Hertzsprung-Russell diagram. It's using temperature versus brightness. And by brightness, we don't mean apparent brightness, because stars are different brightnesses depending on how far away they are. It's the intrinsic brightness of the star.
And the intrinsic brightness is different than the apparent brightness in what way?
Well, just because the star, if you had 2 stars and one's 10 times further away than the other, they might be identical, but the apparent brightness of the one further away would be 100 times less. But their intrinsic brightnesses are the same. They're the same kind of star. If you brought them next to each other, they'd be shining with the same intensity. Okay.
Okay. Yes. All right. We're following with you, Tom.
Yeah. Okay. Let's go on to our corona borealis stars now. So they're very similar. They're carbon stars. They have very little, if any, hydrogen, lots of nitrogen. They're very luminous, as I said. There's a lot more of them known than hydrogen deficient carbon stars, but they're still pretty rare. There are about 150 that are known. And there are probably 1,000 or so in our galaxy. But the main difference between the two types is that the our corona borealis stars are variable. And that makes them easy to notice. So just take a look at this graph at the bottom right, and that shows the brightness, the visual brightness of these stars as a function of time from 1980 to 2000. Now, and you can see that in 1980, the star was shining pretty steadily, had a few little blips, but then suddenly about maybe 83 or 84, it dropped down by 8 magnitudes, which is a factor of about 1,000. So it suddenly became 1,000 times fainter. And then it sort of made its way back up, and then a little later it had a less severe drop, and here's a less severe drop, and then in about 1996 to 97, it had a huge drop, again, about 8 magnitudes. So Edinburgh astronomers like to observe this because they're so large, the changes are so large and they're so unpredictable. So we know a lot about how their brightness varies because they keep track of it. We professional astronomers are delighted that they keep track of it for us. Now, RCB stars have been puzzling astronomers for over 200 years, and I thought it would be neat to show you this paper from 1797 reporting the discovery of the first one, the namesake, the Aurora Borealis itself, by 2 English astronomers. Now, they had been watching it over 10 years. You can see on their notebook on the right, it starts in 1783, actually, the notebook of one of them. And if you look at the part that's outlined in yellow, it says, well, for a while, from 1983 to 1783 to 1795 was pretty steady. But then in the highlighted part, it says not visible with an excellent night glass, therefore less than 11th magnitude, a remarkably rapid disappearance, air clear. Air means it was clear skies. He couldn't attribute it to clouds, for example. So after a few months down at the bottom, it started to return to its normal brightness. And we now understand what's happening in these stars. They're losing lots of gas. And when that gas gets far enough from the star and it's cooled off enough, dust forms, and that blocks the visible light. And then as the dust moves further away from the star, it dissipates and the star becomes visible again.
Tom, a quick question about these early pioneering astronomers here, 1797. So what kind of telescopes were they using back then? The aperture size, because as
well, he says a night glass, so it sounds like something he was holding up to his eyes, like a binoculars or something. I'm not sure it was a telescope. When this star is at its normal brightness, it's a little fainter than you can see with your naked eye, but it's still fairly bright. So I imagine with binoculars or something like that, you would come out. But it must have been tedious. And he was observing from Bath in England, and I'm sure the weather there isn't very good. Maybe that's why his entries are so spaced so widely.
That makes sense. Okay, all right, we're with you, Tom.
Okay, good. Okay, so let's go back to oxygen 18. So at the time we discovered this, nothing was known about oxygen isotopes in these kinds of stars until we found this. So of course we wanted to figure out how this HDC star could have produced so much O18. The O18 could not have been made where we found it in a cool atmosphere on the outside of the star, because in the star it can only be made at very high temperatures, millions of degrees, and that means deeply inside the star. And it's so hot deep inside the star that that nuclear reactions take place. And the most likely way to make O18, given that there's lots of nitrogen there, nitrogen 14 being the most common isotope of nitrogen, is that via this nuclear reaction at the bottom, nitrogen 14 plus alpha particle goes to oxygen 18. What that means, in other words, is that a nitrogen 14 nucleus, and then deep in the star, all the electrons have been stripped off. It's just too hot for the electrons to be bound to the atoms. So there's a bunch of nuclei floating around of various elements, and there are a bunch of electrons all floating around but not bound to one another. So anyway, a nitrogen 14 nucleus bumps into a helium 4 nucleus, which is known to physicists as an alpha particle. They collide at high speed and they get so close to one another that they combine to make O18. So that seemed to be the best way to make it, the most likely way to make it.
Tom, quick question about alpha particles. Now, I've heard of alpha particles in when we watch sci-fi shows like Star Trek. What, in fact, is an alpha particle?
It's the helium nucleus. So a helium has 2 protons. An alpha particle is a nucleus of a helium 4 atom, so it has 2 protons and 2 neutrons, and that's all it is. It's that single particle composed of 2 protons and 2 neutrons, tightly bound, whizzing around, and it just bangs into a nitrogen 14 nucleus, which is 7 protons and 7 neutrons. And if it bangs in hard enough, the result is an oxygen 18. You can't do it you can do it in an accelerator in a physics lab, but you can't do it just in your oven or something like that. The temperatures can be millions of degrees so that these atoms are really whizzing around, and when they collide with enormous force.
Okay. Thank you for clarifying that about alpha particles.
Okay, let's see. There we go. Okay, so where exactly in the star might that happen? Now this shows you where for a red giant star with a mass of the sun. So it's kind of what the sun will be like in about 5 billion years. This is a very complicated diagram. You don't need to understand all of it. And what it's showing is for part of the inside of the red giant star are the amounts of some key elements for this story that I'm telling. And these amounts are based on theoretical predictions from nuclear reaction rates, which are measured in laboratories by physicists. And it's measured for the and they're determined, the model is for the densities and temperatures in the star as a function of where you are on the star. And that's calculated by theoretical astrophysicists. So going to the right here means going toward the outside of the star, going to lower temperatures and lower gas densities. The surface of the star is way, way off this slide. Going in the other direction is going toward the center of the star, but we don't quite get to it. We only get to 0.35. Whoops, go back here. 3.5 of solar mass. So we're still, the center of the star is way off on the left side. And in the vertical direction, it's the abundance of any particular element or the ratio of the abundance of two elements. So for example, nitrogen-14, let's look at that. That starts here. You see it goes up. Some nitrogen-14 is made by certain nuclear reactions. Then in this part of the star, it's pretty stable, but once the temperatures get high enough, it starts dropping because it's being destroyed by something. Here's oxygen-16 here. It gets depleted. And then when you get to this point in the star, its abundance goes up and so on. Okay, let's look at O18. O18 you don't even see on this side of the graph. It comes out of nowhere here and starts to increase, and then it reaches a peak and then it drops. And the reason it reaches a peak is this reaction that I was telling you about that's destroying the nitrogen-14. So as the nitrogen-14 gets destroyed, oxygen-18 is created and that increases. But then look what happens further inside. The oxygen-18 starts decreasing, and that's because the next alpha particle reaction with oxygen-18, which occurs at needs higher temperatures to occur, that destroys the oxygen-18 and creates neon-22. So
okay, Tom, here, as you're taking us on this journey, explaining everything, can we look at just this chart in general? What is this? This is not a spectra. It's not quite an HR.
No, this is a model. This is a model. It's not a spectrum. Okay. It's simply a model of the abundances of certain elements or certain isotopes as a function of location in the star. So the outside of the star is way out on the right. The center of the star is way out on the left. This is the key part that pertains to oxygen-18. And what you see is that at this certain layer of the star, there's this shaded rectangle, which is very deep in the star and really corresponds to a thin shell of gas. There's a lot of oxygen-18. There's no oxygen-18, hardly any oxygen-18 anywhere else but there. So that's the important thing to take out of this diagram. And you can just see how complicated the inside of a star is. And it's amazing to me that people can calculate these things, but they can, and they're actually pretty confident of them.
And so this would be something similar to what's going on in the interior of our star right now.
Well, our sun is not this complicated yet. It'll get that complicated in about 5 billion years. Right now, it's mainly burning just hydrogen to helium.
Right. It's still on the main sequence.
It's called the main sequence, which is just the hydrogen burning sequence. But later, it'll get into a phase like this, and it'll start getting very complicated.
Okay. Okay.
Yeah. Okay. This isn't a star like the sun in its red giant phase.
Thank you for clarifying that.
Okay. Very good. Okay. So anyway, when Jeff and I saw that diagram or others like it, we had the idea that what we'd found was this O18 shell, that it was somehow now on the surface of the star. Now, how could it have gotten there? It couldn't have migrated there, because if it had migrated there from the inside, it would have mixed in with all the gas it had to pass through, and the oxygen-18 would have been diluted. So it must have been that we thought it must have been that this star, HD 137613, had somehow lost its outer layers precisely down to that O18 enriched layer. And somehow that layer had cooled off from the millions of degrees that were needed to make the oxygen-18 to thousands of degrees where carbon monoxide could form, because molecules don't exist at millions of degrees. They only exist at thousands of degrees and less, a few thousand even. So even though that seemed far-fetched, nothing else made sense. So in our first paper, which I show here at the top, reporting this discovery, that's what we tentatively suggested. If you read the part of the abstract, it says, some mechanism of enhanced mass loss must be involved. That's in the second and third lines of the abstract. Okay. All right, so that was our idea. Well, it's one thing to have a theory. It's another to test if it's correct. Clearly, any explanation must be tied to the issue of whether HD 137613 is unique. If our explanation was correct, it seemed to us that that star would certainly be unique, because it seemed absurd to think that every single hydrogen deficient carbon star would lose its outer part precisely down to that layer and not further. It just didn't make any sense that that would be. So we thought the star would have to be unique if our idea was right. So to check, sorry, this is the slide I should have been referring to. So anyway, to check if that was unique, we applied for time at the Gemini South Observatory to use Gemini's near-infrared spectrograph GNIRS to observe the remaining 4 HDC stars. But we didn't just ask for time for that. We also asked for time to measure the CO spectra of a few R corona borealis stars, ones that were in the southern sky, ones that were cool enough that they should have lots of CO in them, so we could look for the isotopic species. And we were granted that time. And so about a year or so after the discovery, we got the observations. I reduced them in my office, and this is the result. The result was that every star that we observed in that sample had huge excess of oxygen 18. Now, the amount of excess varied from star to star, but they all had huge excesses. And here I'm showing you spectra, like the ones I showed before, of the champions, so to speak, of each of the class. So here's the champion R corona borealis star up here, WX corona australis. Here's the O18 band here, here's the next one, here's the next one. And to compare the abundance, you really have to compare this band with this band. So it looks like they're almost the same strength. So in this, there's about the same amount of O18 as O16, because the C12O18 and the C12O16 bands are the same. Now look at this hydrogen deficient carbon star. This one is the real champion of all we've seen, because here's the first carbon 12O18 band. And if you compare that with this one, it's a lot stronger. So we think there's 2 or 3 times more oxygen 18 in that star than there's oxygen.
As you're showing us the differences between these 2 points in the spectra, where one is stronger than the other, what is it exactly that you're looking at in the spectra that indicates one line is stronger than the other?
We're looking how deep it is, because the star, without the carbon monoxide, the star signal would be here. With the carbon, there are also a lot of other absorbents to other molecules, but with the carbon monoxide, the light gets blocked. A lot of the light gets blocked, and it depends on how much carbon monoxide there is. So this tells us how much carbon 12 oxygen 18 there is by how deep this dip is. And this tells us how much carbon 12 oxygen 16 is by how deep this dip is, and the other dips as well.
Okay, that makes sense.
Here's another carbon 12. Look how strong this one is.
Because it has a deeper dip.
Yeah, that means there's more carbon 12 oxygen 18 absorbing the light from the star. That carbon 12 oxygen 18 is located on the outside of the star, so it absorbs the light coming out from the middle of the star.
So you said that you were reducing this data yourself in your office. Can you, what does that mean to reduce?
Well, when you get data, you make many different measurements of a star. Usually you might take several, say 3 or 4 minute exposures. You have to combine them. You often put the star at different parts of this, different positions of the slit of the spectrograph. So you have the spectra in different parts of the array of the detector array that's measuring light. You have to correct for the atmosphere absorption. Not all the light from the star gets through, because the Earth's atmosphere is also absorbing light at different wavelengths. The detectors don't have identical response. You know, a detector on one side of the array might be responding more strongly to light than the other one is, even if it was seeing the same amount of light. So there are all these effects to correct for. So you don't usually just see the result right off the bat. You have to go through a lot of processes to remove all those effects.
How long does it generally take for the data that you're sharing with us here, for example? How long would the reduction take? And do astronomers normally do their own data reduction?
It's a mixture. We have at Gemini, we have pipeline reductions for some types of spectroscopy. In this case, we didn't. This was back in 2004, 2005. We did not have that at the time. I reduced these by hand. It took me maybe 2 or 3 hours per spectrum to do. So I probably spent a day or two working on all these 9 spectra that we obtained during this observing run.
Okay.
It's very exciting to see the results pop out.
I can imagine.
Okay, I will continue, I think. Okay, so our initial hypothesis was wrong, because we would have expected not to have seen it again. We would have thought that HD 137613 was unique, but it wasn't. But discovering this excess O18 and RCB stars led to a breakthrough in our understanding, and that was because there are so many of them, and because their brightness variations are so peculiar. Astronomers have been studying who study how stars evolve, have been trying to figure out how RCB stars form for a long time. And basically, people had come up with two likely possibilities. And this paper, written about 20 years ago, is one of the many that proposed that RCB stars are produced by what's called a final flash. It's a final flash of nuclear reactions on the surface of the star at the end of its red giant phase, just before the star becomes what's called a planetary nebula, which, by the way, is no relation to planets. Now, that could explain the size and the brightness of the stars, as it says up at the top of the slide. And it could even explain the elemental abundances, not the isotopic abundances, but the elemental abundances. That is when you add the abundances of all the isotopes of each element and together, and then you compare them. However, this kind of a flash would not be able to produce O18 that's made from nitrogen-14. And that's because models show that either the nitrogen-14 is completely converted to neon-22, so there's no intermediate O18 left during one of these flashes, or there's some hydrogen nuclei, protons basically, that are also mixed in with all this flash. And those nuclear reactions with O18 and protons during the final flash also quickly destroy any O18 that's made. There's another problem with this model too, and that's that there's a modern example of one of these final flashes that's been observed, an object called Sakurai's object, which went off in about 1997, and it was found to have lots and lots of carbon-13. And we know that from all the observations of all of these HDC stars and the RCB stars, that none of them have any carbon-13. So this did not seem to be the way that they could be made.
So Tom, when you're coming up with conjecturing what's going on based on your data, and you're working with your collaborators, do you also work with other scientists and talk about what you're finding, even if you're not on the same team, just to help gain better understanding?
We do, once we have some idea where to go. At this point, we had not talked to too many, but as you'll see, we now get involved with a lot of other scientists. Because the other possibility, which was also proposed in the 1980s, is this is the paper where that proposal was made. It was totally different, and it suggested that our corona borealis stars are created by the mergers of two objects known as white dwarfs. And if you read the top, an our Corobor star is the result of the merger of two white dwarfs, a helium white dwarf and a carbon-oxygen white dwarf. I'm not going to get into what these are at the moment, but accreted helium is ignited on the more massive carbon-oxygen white dwarf, and the carbon-oxygen white dwarf expands and cools and becomes an our corona borealis star. Okay, so that's quite different than a final flash. They're both very violent events, but they're quite different. So, it sure jumps a lot. Okay, so here we are. Perhaps you've heard about white dwarfs before. Let's just review their basic properties. So one of the first white dwarfs found is called Sirius B. It's a companion to Sirius, which you probably know is the brightest star in the sky. Sirius B is a lot dimmer than Sirius A. You can barely see it in this image. The arrow there is pointing to it. Now, when its discoverers looked at the spectrum of Sirius B, they were shocked to see that Sirius B was hotter than Sirius A. Now, hotter generally means brighter, but this object was very faint, yet it was the same distance as Sirius A, since it was known to be orbiting Sirius A. So the only explanation had to be that it was much, much smaller than Sirius. So we now know that that's what a white dwarf is. It's what the sun is going to become in about 5 billion years. It's what most stars will become. The sun is going to lose about half of its mass when it's a red giant, and the remaining gas will be compressed by gravity until it's about the size of the Earth. So a white dwarf has a composition of the inside of a star, whatever's left after the red giant phase, and it's extremely dense. If you took a teaspoonful of it, if you could, and you put it on the surface of the Earth, it would fall right through the Earth to the center.
So you're saying just a teaspoon of this white dwarf material would be enough to
The
uh,
Earth, the Earth's
tear
surface
through
could
the
not
Earth?
support it. Yeah, the Earth's surface could not support it. It would just fall right down to the center, or it would oscillate back and forth between one side and the other until it finally stopped in the center.
Okay.
Amazing objects, and they're not the densest objects in the universe either, but they're pretty dense.
So, so our sun is not going to become a black hole or anything like that. It's going to
No,
become
it's going to become a white dwarf.
a white dwarf. Now, that's based on what the final outcome of a star's life is determined by its mass.
That's correct. That's correct. Stars that are more massive than about 8 times the mass of the sun end up exploding as supernovae. I think those become neutron stars, and if they're somewhat more massive than 8 solar masses, then the core collapses after the supernova explosion or during it and becomes a black hole. I don't remember exactly what the limit is, something like 15 times the mass of the sun. Okay, so that's what a white dwarf is. But why might 2 white dwarfs merge? They're all over the place in the galaxy. What would make them merge? Well, you might have heard that most stars form as parts of double, triple, or even more multiple systems. And in some cases, pairs of stars can form very close together. And most stars become red giants and then white dwarfs. And then in some cases, they can merge if they started out close enough together. That process of turning into a red giant tends to bring them closer together because there's a lot of friction as one's orbiting the other. And so it brings them closer and then they merge. And in these mergers, as it said in that paper, the less massive white dwarf is torn apart by the more massive white dwarf. And as you can imagine, it's a very violent event, creates very high temperatures. So Jeff gathered into our team some theorists who actually model collisions like this. And he gathered into our team astrophysicists, or 1 or 2 astrophysicists, to calculate from the temperatures and densities during the merger what elements in their isotopes are produced. And as you can imagine, these are both very complicated calculations. But the results indicate that the environment of this dense and hot but cooling atmosphere of the merged white dwarf can produce a lot of oxygen-18 via this alpha reaction that I showed you earlier, and that some of the O18 is retained because the gas cooled down before the O18 is converted all to neon-22. All of this went into a paper that our large team published in 2007. And briefly, I guess since I'm running out of time, despite there being a lot of details to work out and many more questions to answer, this merger scenario has now been generally accepted as the route by which all of these bizarre R Corona Borealis stars and hydrogen-deficient carbon stars form. So what has happened? Go ahead.
So, sorry, pardon me, Tom. So are you saying that you were part of the group, the team that discovered this new process?
Mm-hmm, mm-hmm. I was the lowly observer. I didn't do any of the thinking about what it meant.
But still, being a part of the team had to feel amazing to contribute to something that we never knew before. That's
right. Yes. Yeah. Well, that's astronomy is all about that. I think everybody has that. Who's doing astronomy has that feeling. We're all learning new things all the time, and of course that leads to more questions. And so let me just tell you a little bit about what happened since then. So other astronomers have subsequently confirmed that our measurements, the O18 is very abundant in these stars. We've observed more R Corona Borealis stars in our galaxy. And recently, using Gemini South, we observed an R Corona Borealis star in each of the 2 satellite galaxies of the Milky Way, the large and small Magellanic Clouds, which are here. There's the large one here. Here's the small one. We're looking through our galaxy, so we see lots of foreground stars. Here are the spectra. You can see these little dips. Here are the C12O18 bands in the large cloud object. Here they are in the small cloud object. Those stars are much further away from us, so they're much fainter, but these spectra clearly show the C12O18, and the excesses of O18 aren't as big as the champion R Corona Borealis star that I showed you in the Milky Way, where the abundances are about equal, but still they're a lot more than the normal amount of O18. So this finding strongly suggests that white dwarf mergers are a universal process for making R Corona Borealis stars and probably HDC stars as well. And making lots of O18 is not just limited to R Corona Borealis stars and HDC stars in our Milky Way. It occurs throughout the universe. So I guess that's the story of how this accidental discovery led to an explanation for the origins of two unusual types of stars. I'd be happy to take questions. You know, as we just discussed, I've been involved in many much more conventional research programs, which have sort of a logical start and end. But I've also been involved in a few unexpected discoveries of this kind, and they're definitely fun to be part of, and they're part of what makes astronomy so exciting. So I'll stop there, Jamika. Thank
Excellent.
you all for being here.
Thank you so much, Tom, for sharing with us. It definitely seems an exciting journey, especially being an observer, but going along with this whole adventure and then being able to share it with us is really quite thrilling. And so now we have from our YouTube live world, Alyssa Leilani Grace is here to share with us a few comments and maybe a question or two from our YouTube audience. Alyssa.
Aloha Kako. We just have some pretty fun comments in the chat right now. Thank you to everyone for participating in our YouTube chat. Some of the comments include just some hellos from different parts of the world. We have Michael Mosby from Memphis, Tennessee, and Dale and Harriet from Louisiana.
Oh, wow.
Yeah. Peter Michaud mentioned early on in our chat, in reference to the Red Sox in your email, he said, "Go Sox." And Jerry mentioned that this live event has been very big brain for him. And Dale and Harriet agreed, saying that they get the same feeling when talking to their son, Trent, who got degrees in both physics and astronomy. And we also have quite a few jokes about white dwarf stars,
yeah,
making the Earth's surface go down, about mommy white dwarf and daddy white dwarf attracted to each other to do the white dwarf merger.
Yes, right. You wouldn't want to be close to one of those events.
Well, thank you so much, Alyssa, for sharing with us the comments from our YouTube live audience. And as we wrap up here, I'd like to first say thank you to everyone in our YouTube live audience, and to again return to our guest, our special guest today, Dr. Tom Geballe, emeritus astronomer at the International Gemini Observatory.
Thank you.
Next week, Alyssa Leilani Grace will be your host, and she will have with her Joy Pollard, who is the multimedia and graphics designer and tour coordinator here at the International Gemini Observatory. They will be discussing the Gemini Observatory virtual tour. So I hope you can join us next week for our upcoming YouTube Live event. In the meantime, we'd like to say thank you to everyone, which is a big mahalo. And I'm going to send it back over to Dr. Tom Geballe, our science guest, to give us our last parting words. Tom.
Well, thank you very much, everyone who bore with me as we discussed R-core Bohr stars. I hope it wasn't boring. I hope you learned something. I hope you weren't snowed too badly by all this spectroscopic detail, but it really is, to me, that's spectroscopy is much more exciting than pictures, although pictures are beautiful. Spectroscopy tells you things that you can't learn from pictures, and that's why I really enjoy being a spectroscopist doing astronomy. Thank you all very much for joining in today.
Thank you so much, Dr. Tom Geballe of the International Gemini Observatory, a program of NSF's NOIRLab. We'll see you here next week with Alyssa Leilani Grace and Joy Pollard. Mahalo and aloha.